Welcome, everyone, to another deep dive here on artificial intelligence, unorthodox lessons, the podcast where we like to take a look at some of the most essential and practical topics in AI, and we try to unpack them so that you can get well informed quickly but thoroughly.
And we're sponsored by NotionWave, a leading AI company with solutions for research and education and much more.
Yeah, they're doing some really interesting stuff over at NotionWave, but today we are venturing into a fascinating story, a real-world story about building AI that actually works.
Right. We're going to forget about abstract theories just for a little while here and look at a real project that a machine learning team at a startup did.
Yeah, this is really cool.
They had to create a gesture recognition engine for a smart gadget.
Oh, wow.
And it was so clever that it eventually found its way to Facebook.
Oh, wow. That's a pretty good pedigree right there.
Yeah, so this episode is your backstage pass to understanding how complex AI systems are actually built.
Yeah, and we're going to dissect their Ensemble classifier, which combines multiple learning models to achieve better performance than any of the models could do by themselves.
That's right.
We're going to uncover the key decisions and the aha moments that led to their success.
And no advanced technology is needed here. We're going to make it clear and engaging for everyone.
Absolutely. So this startup was operating in the early days, and they had all kinds of challenges that you don't really read about in textbooks.
That's right. Messy, real-world challenges.
Yeah, so let's just dive right in.
Okay.
What was the first big hurdle they faced?
Well, the smart gadget they were developing was designed to recognize hand gestures just by interpreting muscle signals from sensors that would be worn on the forearm.
Oh, wow. So almost like an EMG or something.
Yeah, exactly.
Oh, that's interesting. Okay.
But the problem was that the product was in such an early stage of development that the data they were getting from their prototype was pretty questionable.
Yeah, well, especially with EMG data too, right? I mean, it's so susceptible to if you move the sensor just a little bit or if the connection's bad or something, it can be really, really noisy.
Exactly. And to make matters worse, they hadn't even finalized exactly which hand gestures the gadget was supposed to identify.
Oh, so they were kind of, flying by the seat of their pants a little bit.
They were. And on top of all of that, the usual advice that you hear in AI, which is just collect tons and tons of data.
Right, just get more data.
Yeah, it just wasn't practical at this early stage because they didn't want to waste a bunch of time collecting data for a product that might change directions.
Right. Yeah, absolutely. I mean, especially at a startup, you've got limited runway. You don't want to be spending all your time collecting data that you might not even use.
Exactly.
So how did they deal with all this uncertainty?
Well, they took a really clever approach.
Okay, I like Cliff.
Instead of trying to build one incredibly powerful AI model
Right.
with all this unreliable data, they decided to use something called an ensemble method.
Okay, ensemble method. So that means multiple models instead of just one big one.
That's exactly right.
Okay, interesting. So they're kind of hedging their bets a little bit.
Yeah, you could say that. And they decided to start by building something called a base
A
classifier.
base classifier.
Okay. And a really important point here is that they weren't aiming for perfection right out of the gate.
Okay, that makes sense.
They knew that the data was unreliable and that the goals of the project might change.
Right.
So they just wanted to build a simple model that was better than random chance.
Okay, that makes sense. Get something working and then iterate on it.
Exactly. So they chose a vector classifier using something called cosine similarity.
Cosine similarity. Okay.
And that was their base classifier. And it performed okay. I mean, it definitely wasn't ready for prime time,
Right.
but it gave them a solid foundation to build on.
I see. So they weren't trying to build the perfect model right out of the gate. They were just trying to get something that worked reasonably well and then iterate on it.
Exactly. And that's a really important lesson for anybody who's working in AI,
Yeah, don't let perfection be the enemy of good.
right?
Yeah.
Sometimes a simple model is all you need to get started.
Yeah, absolutely. Especially if you're working with limited data or if the problem that you're trying to solve is still evolving.
Absolutely.
So they had their base classifier.
Yes.
Now what did they do?
Well, when you talk about ensemble methods, you often hear advice that says you should combine lots of different types of algorithms.
Right, kind of get a bunch of different perspectives.
Exactly. But this team decided to do something a little bit different.
Okay.
Instead of using lots of different algorithms, they decided to use the same algorithm for all of their base classifiers.
Okay, so they had a bunch of models and they were all using that vector classifier with the cosine similarity.
That's right.
Why did they do that?
Well, they actually took inspiration from some really well-known ensemble algorithms like random forest and AdaBoost,
Okay.
which both use multiple copies of the same algorithm.
So random forest has a bunch of decision trees.
Yes, exactly.
And AdaBoost, I think, uses a bunch of really, really simple decision trees.
Yeah, just one-level decision trees.
Interesting.
And they realized that by using the same algorithm for all of their base classifiers, they could actually get a really deep understanding of how that algorithm worked.
Okay.
And that allowed them to fine-tune the ensemble in a way that wouldn't have been possible if they were using a bunch of different algorithms.
So they were able to like really get under the hood of that algorithm and like tweak it and optimize it in a way that they couldn't have done if they were using a bunch of different algorithms.
Exactly. It's kind of like the difference between being a jack of all trades and a master of one.
Right. Okay. That makes sense.
Sometimes it's better to really deeply understand one thing than to have a superficial understanding of many things.
Yeah, absolutely. And I think that's a really important lesson for data scientists and machine learning engineers in general. Like, you don't need to know every single algorithm out there.
You're right.
It's more important to have a really deep understanding of a few key algorithms.
Exactly.
Yeah.
And to be able to apply them effectively.
Yeah, absolutely. So they had this team of base classifiers now all using the same algorithm.
Right.
And they were all performing adequately, but not exceptionally.
Right.
So the next big challenge was figuring out how to combine their outputs,
Right.
how to aggregate them,
Exactly.
so they could make a really high-performing prediction.
Right. Because ultimately they want one prediction
Right.
from the whole ensemble.
Right, exactly. Okay, so how do they do that?
Well, there are three main strategies that are used to aggregate base classifiers.
Okay.
The first is called attention mechanisms.
Okay.
It's also known as boosting.
Boosting.
And in boosting, the algorithm learns which base classifiers are performing well and which ones are performing poorly.
Okay.
And it gives more weight to the predictions of the classifiers that are doing well.
Oh, that's interesting. So it's like kind of like a weighted average?
Exactly. And it allows the ensemble to improve over time because it's focusing on the classifiers that are doing the best.
Okay, that makes sense.
The second strategy is called data split
Okay.
or bagging.
Bagging. Okay.
And in bagging, you train multiple classifiers on different subsets of the data.
Okay.
And then you average the predictions of all the classifiers.
So it's like getting a second opinion.
Exactly. It's like you're getting a bunch of different opinions, and then you're averaging them together.
Okay.
And that helps to reduce the variance of the ensemble.
Okay, so it's like it makes the predictions more consistent.
Exactly.
Okay.
And the third strategy is called model stacking.
Model stacking.
And in model stacking, you first train your base classifiers on the full data set.
Okay.
And then you use another model called a meta model
A meta model. Okay.
to learn how to combine the predictions of the base classifiers.
So it's like a model of models.
Exactly.
Okay, interesting.
So the meta model is learning how to best weight the predictions of the base classifiers.
Okay, that makes sense.
So those are the three main strategies.
Right.
And the startup had to decide which one was going to work best for them.
Right, given their unique challenges.
Exactly.
So which one did they choose?
Well, they actually ruled out boosting and bagging pretty quickly.
Okay, why is that?
Well, boosting is a sequential algorithm,
Okay.
which means that each classifier is built on top of the previous one.
Okay.
And that would have made it really difficult to adjust the individual base classifiers for all the different ways that people might wear the gadget.
Oh, right, because remember they had to deal with all the different orientations and rotations.
Exactly. And if you have a sequential algorithm, it's really hard to go back and tweak one of the classifiers in the middle of the sequence without affecting all the other classifiers that come after it.
Right, that makes sense. Okay, so what about bagging? Why didn't they choose that one?
Well, bagging is really good at reducing variance.
Okay.
But in this case, the team was more concerned with bias.
Okay, what's the difference?
Well, variance is basically how much the predictions of a model change when you train it on different data sets. So a model with high variance is going to make very different predictions depending on the data that it's trained on.
Okay.
A model with low variance is going to make pretty much the same predictions regardless of the data.
Okay, that makes sense.
Bias, on the other hand, is basically how accurate the model's predictions are on average.
Okay.
So a model with high bias is going to make predictions that are consistently wrong in one direction.
Okay.
A model with low bias is going to make predictions that are on average correct.
Okay, so it's like if you're trying to hit a target variance is how spread out your shots are.
Right.
And bias is how far off from the center of the target you are on average.
Exactly.
Okay, that's a great analogy.
So in this case, the team was building a population model,
Okay.
which is a model that's designed to perform well for a large group of people.
Okay.
And they were concerned that if they used bagging, they might end up with a model that was really good at making consistent predictions.
Okay.
But those predictions might be biased in a particular direction.
Okay, I see.
So they decided to go with model stacking instead,
Okay.
which gave them more control over the bias of the ensemble.
Okay, that makes sense.
But they didn't just use standard model stacking.
Okay, what did they do?
They actually added a really interesting twist.
Okay, I like twists.
They created two separate models,
Okay.
a population model
Okay.
and a personalized model.
A personalized okay, so two different models working together.
Exactly.
Okay. How did that work?
Well, the population model was designed to be really good at making predictions for a large group of people.
Okay.
And it was trained on a large data set of data that was collected from a lot of different users.
Okay, so it's kind of like the general model.
Exactly.
Okay.
And the personalized model was designed to be really good at making predictions for individual users.
Okay.
And it was trained on data that was collected from that specific user.
Okay, so it's like a custom model for each user?
Exactly.
Okay, so how did they combine the predictions of these two models?
Well, that's where the meta model came in. The meta model was trained to figure out how to best combine the predictions of the population model and the personalized model.
Okay, so it's like the meta model is the conductor of the orchestra.
Exactly.
Right.
And the meta model was a really sophisticated piece of machinery.
Okay.
It used a probabilistic classifier,
The probabilistic classifier. Okay.
which basically figures out how confident each base classifier is in its prediction.
Okay.
And it also used a voting mechanism
A voting mechanism.
to combine the predictions of all the base classifiers.
So it's like the meta model is taking a vote from all of the base classifiers
Yeah.
and then weighting the votes based on how confident each classifier is.
Exactly.
Okay, that's really clever.
Yeah, it's a really elegant solution.
Yeah, and I think it's a great example of how you can be really creative with your aggregation strategy.
Right, you don't have to just use the standard textbook methods.
Exactly. You can tailor your approach to the specific problem that you're trying to solve.
Right.
So they had their ensemble of base classifiers. They had their aggregation strategy, yes, but they still had one more big challenge to overcome.
What was that?
Well, remember that users could wear the gadget in all sorts of different ways.
Oh, right, the different orientations and rotations.
Exactly. And that could really mess with the predictions of the models.
Yeah, because the muscle signals are going to look different depending on how the gadget is being worn.
Exactly. So how did they deal with that?
Well, they actually put a lot of effort into developing an algorithm that could adjust the base classifiers on the fly.
Oh, wow. So like every time someone put on the gadget, the algorithm would adjust the models to account for how they were wearing it.
Exactly.
Okay, that's really impressive.
Yeah, it's a really good example of how important adaptability is in real-world AI applications.
Yeah, because in the real world, you can't always control the environment that your AI is going to be operating in.
Right? You have to be able to deal with unexpected changes and variations.
Exactly. And I think this is something that a lot of people who are new to AI don't really appreciate. They think that you just build a model and then you deploy it and then you're done.
Right.
But in reality, it's a lot more complicated than that.
Exactly.
Yeah.
You have to be constantly monitoring your models and making sure that they're still performing well.
Right. And you have to be able to adapt them to new situations.
Exactly.
So this whole story is really about the power of ensemble methods
Yes.
and about the wisdom of weighted crowds.
Right.
Which is this idea that you can often get better predictions by combining the predictions of multiple models than you can by using just one model.
Exactly.
And I think that's a really powerful idea.
Yeah, it's a really important principle in machine learning.
Yeah, absolutely. And I think it's something that we can all learn from,
Right.
whether we're building AI systems or just making decisions in our everyday lives.
Right. It's often helpful to get multiple perspectives.
Yeah, absolutely. And to weigh those perspectives based on how much we trust the source.
Right.
So let's recap what we've learned today. We started by talking about this startup that was building a gesture recognition system for a smart gadget.
Right.
And they were facing all these challenges with limited data and unclear objectives.
Right.
And they decided to use an ensemble method to overcome these challenges.
Right.
And they made a few key decisions that really helped them to succeed.
Right.
First, they chose a simple base classifier that they could really understand.
Yeah.
Second, they used the same algorithm for all of their base classifiers so that they could really fine-tune the ensemble.
Okay.
Third, they used a really clever model stacking approach that allowed them to address both bias and adaptability.
Right.
And all of this was inspired by the wisdom of weighted crowds.
Yeah, and I think their story is a great reminder that you don't always need to have the perfect solution right away.
Right.
You can start with something simple and then iterate on it over time.
Exactly. And you can use the power of ensemble methods to combine the strengths of multiple models.
Exactly.
So if you're working on an AI project and you're feeling stuck.
Remember the story of this startup.
Right.
And don't be afraid to think outside the box.
Yeah, absolutely.
And if you're interested in learning more about ensemble methods and other essential topics in AI,
Yeah.
be sure to follow Artificial Intelligence Unorthodox Lessons.
We've got some really great episodes coming up.
That's right. We'll be diving into some of the most cutting-edge topics in AI.
And we'll be talking to some of the leading experts in the field.
So be sure to subscribe so you don't miss an episode.
Thanks for joining us today.
Yeah, it was great chatting with you.
See you next time.